Hi everybody, welcome back. In this video we're going to be looking at areas and distances. And what you see on screen here at the very top is these three depictions of areas that it can be found by using a geometric representation. So for example, the very first depiction of the area underneath the graph of f of x on your left hand side is a rectangular shape. Now, since we have a rectangular shape, we know that the area of any rectangle can be thought of as length times width. And if we know the function height, that means we will know the length value for, or the width value for this particular area. And looking at the interval from a to b, that's going to give us some length for the area, which means we will be able to find the numerical value. If we look at the second graph, the one in the middle where we have a semicircle, since we have a semicircle, we can calculate the area of a circle by using the geometric representation of pi r squared. Once we find that area in accordance to its radius, we can then go through and take half of that area because we're dealing with a semicircle. And looking at the final graph on the right hand side, we see that the area underneath the function f of x bounded by the interval from a to b can be split into different regions. However, each region can still be calculated by taking a geometric representation. We can use triangular areas here, otherwise calculated by half base times height, in order to find the total area underneath that curve. And this is what we want to base our work off of when we're talking about areas underneath the curves, and in this case particularly for functions f of x. Now, we're going to get more intricate than these particular examples, meaning that we're going to need to find areas underneath these functions where these functions are not just linear functions, they're not just circular functions or these arc functions, but they're going to have more of polynomial shapes, more of rational function shapes, and we are still concerned with finding the area underneath those curves. And in order to extract the conversation into those particular areas, we're going to focus on this function that I gave you here, function f of x. And this is the function f of x, which is depicted in green. It's given from the interval from a to b, and then I've subdivided I've subdivided the interval from a to b into 8 equal pieces. So what we'll do here is we will call each subdivision here delta x. In other words, every single subdivision has this width, delta x. And the way that we get delta x is by taking the length of the interval, b minus a, and then dividing it by an n value. And this n value is a typical n value that we want to then produce. Do we want the interval to be subdivided into 7 pieces, into 8 pieces, into 9 pieces, into 100 pieces, so on and so forth? We then need to come up with that number. In general, though, we always keep it as n, just by saying that we're subdividing this into n subintervals. And in order to approximate the area underneath the curve f of x from the interval from a to b, we're going to subdivide that area into these small subintervals, and within these subintervals we're going to start creating rectangles, and these rectangles are going to have a certain height. For this depiction, the heights are going to be the leftmost endpoint on each subinterval. And you can see here that what I'm doing is I'm highlighting this point on the leftmost endpoint for each subinterval. And what you're going to notice is that the height of each rectangle there corresponds with, again, the leftmost endpoint on that interval. So this first leftmost endpoint is going to be f of a. The second leftmost endpoint is f of x sub 1. Then the third is f of x sub 2. And we keep going on, so on and so forth, all the way till we get to the very end of this interval where we'll have x sub 7. Now, this is known as your left-hand sum approximation, or left endpoint approximation. So left endpoint. And again, if we want a left endpoint approximation, we're going to denote this as L sub n. Again, left endpoint, n is going to denote how many subintervals we want. And we're going to take the summation of all of these rectangular areas. So taking the summation of all of those rectangular areas, I'll save that sigma notation for a bit. We're going to take delta x, that's the first delta x, the width from a to x sub 1, times its height, which is going to be f of a. F of a can be represented as x sub 0, or as we like to call it, f naught. The second area for the second rectangle is going to be calculated by, once again, delta x, but this time multiplied by the height of the leftmost endpoint, which will be f of x sub 1. And we keep going in this manner until we capture all of the subintervals, or the areas that have been subdivided. And what we're left with here, delta x multiplied by f of x sub n minus 1. Because again, we're not going to the very end point of the end of the interval, which is b. We're going to the one right before it, x sub 7, and that's going to produce the last height of the rectangle. Therefore, the function value will be f of x sub n minus 1. And this summation can then be represented by the summation of I beginning at 1, stopping at n, for the function f of x sub I minus 1 multiplied by delta x. And this is your left endpoint approximation. So anytime that we're looking for these left endpoints, this is what we are looking for. So this is your L sub n. And again, this is the important part. Perfect. Now, what if we wanted to do the same thing now, but instead we wanted to work with right endpoints? So to take this into consideration then, every single right endpoint on the subintervals is then going to determine the height of these rectangles. So I go to the first interval, the rightmost endpoint, that's going to be the height. Go to my second interval from x1 to x2, the rightmost endpoint is the height of that rectangle. Go to the third interval, the rightmost endpoint is the height of that rectangle. And we keep on repeating this over and over and over again. And you're going to see that the area here for the rectangles does approximate the area for f of x underneath f of x from a to b. However, in this particular case, it over approximates versus the previous example in the left endpoint sum where it under approximated. Now, it's not always the case that the left endpoint will under approximate and the right endpoint will over approximate. Sometimes they might actually switch, in which the left endpoint will over approximate and the right endpoint will under approximate. So we must remain flexible with that topic. So in this case, R sub n, the right sum of these endpoints, is then going to be calculated by, once again, delta x, because delta x is the length of each interval, or each subinterval, which means we're going to have delta x multiplied by the height of the very first rectangle, but the height is determined by the rightmost endpoint, which will be f of x sub 1, plus delta x multiplied by the second-most endpoint on the right is f of x sub 2. We can keep going, delta x, f of x sub 3, plus, and we keep going till the very end, that we get delta x multiplied by my function. In this particular case, it is the very last value, b. But b can be thought of as x sub n. So here we have delta x multiplied by f of x sub n. And if we want to write this in condensed summation notation, then we're going to have the index beginning at 1, stopping at n, and this is going to be 4 f of x sub I multiplied by delta x. And you're going to notice the similarities between the left endpoint and the right endpoint, that both of these values, both of these approximations are doing just that. They're approximating the area underneath this curve. Now, two more different topics that we're going to look at that are still going to get us approximations. The next topic that we're going to look at here is going to be upper sums. So upper sum approximation. When we want to take the upper sum for this approximation, what we're going to have to do is we're going to have to individually go into each interval and identify what is the highest point in that interval. Once we're able to find what is the highest point in that interval, that will then create the rectangle for that interval. And hence we have those upper sums. So, in each interval, the largest f of x sub I star, and this is just some random sample point that we take in each subinterval. In each interval, the largest f of x sub I star determines the height of each rectangle. Alright, so in each interval, the largest f of x sub I determines the height of each rectangle. And that's what I have depicted here on this graph here. Is that I went to each interval and I determined what is the largest height in that interval. From there, I just created the rectangle that corresponds to the height that was then created there, or that was identified. Similarly, we can have lower sums. So these lower sums, it's very similar to the upper sums. However, when we want a lower sum approximation, we go to the interval and we identify the smallest f of x value that is then produced on that interval, and that then creates our height for the rectangles. So let's write that up. In each interval, the smallest function value determines the height of each rectangle. And so when we start then going through these approximations, we want to then identify, well, we do have these upper and lower sums, but why are they beneficial to us? Well, if we then consider A to be the area under f of x that is bounded by x is equal to a and x is equal to b, then what we get is that the lower sum creates this bound for the area, or this lower bound for the area, and the upper bound is created by the upper sums. And so once again, we come across this conclusion to say, well, even though we might not know what the area underneath the curve is, just by taking the lower and the upper sums, we're then going to be able to create a bound for this area to definitively say that the area amount must exist between the lower and the upper sums. And so that's what we want to see here. That is why we want these upper and these lower sums. So let's go ahead and let's work on an example where we're going to use some left endpoints, right endpoints, upper sums, lower sums to find a certain approximation for an area. Alright, so here's the example that we're going to be working with. The example says, given the function f of x, which is equal to sine of x, on the interval from 0 to pi, find the left endpoint sum approximation of L sub 4, the right endpoint approximation of R sub 4, the upper sum and the lower sums with n is equal to 4. And so what I'm going to do really quickly is I'm going to start looking at the graph that is given to us on the interval from 0 to pi, and then I'm going to go with my subdivisions of n is equal to 4 before I go through any of the left, right, or upper or lower sums. Alright, so that's what I want to do first. And what I'm going to do is I'm just going to draw the picture really quick, and we'll get to it from there. Alright, so here's my function for sine of x. And again, it's on the interval from 0 to pi. And what I'm going to do is I'm going to calculate my delta x first. So my delta x is going to be b minus a. So my b value is pi, my a value is 0. And so we do pi minus 0 divided by the number of subintervals that we want, which in all of the approximations, it's going to be n is equal to 4. So I want to subdivide by 4. Which means every single increment will be a pi fourth increment. So starting at 0, we increment to pi fourths. We increment another pi fourths. This gets us pi halves, and we increment another pi fourths, which gets us 3 pi fourths, and then lastly, pi. And so again, all of these intervals, they're all delta x. Alright, so that's good to see there. Now, I want to work with my left endpoints. So for my left endpoints, again, I'm going to subdivide here. And on each interval, I'm going to go to the left endpoint. Left endpoint, that creates the height. Left endpoint creates the height. Left endpoint creates the height. Left endpoint creates a height for that rectangle. So the area here is going to be here. And as you're going to see, it serves as an approximation. It's not the best approximation, but it's an approximation that will help us. So this is going to be L sub 4. And I want my delta x multiplied by my f of x naught plus delta x multiplied by f of x sub 1 plus delta x multiplied by f of x sub 2, and finally delta x multiplied by f of x sub 3. Remember, all the delta x's are exactly the same. That delta x is pi fourths. F of x evaluated at, f evaluated at x sub naught, that's going to be f of 0. So the function is just sine, so that's going to be sine at 0. The next function evaluated at f of x sub 1, that's going to be sine at pi fourths. The next function, f of x sub 2, that's going to be sine at pi halves. The next function is going to be sine at 3 pi fourths. Now, we know here that sine at 0, that's going to be 0, which means we get 0 plus sine at pi fourths. Sine at pi fourths, that should be root 2 over 2. Sine at pi halves, that's 1. Sine at 3 pi fourths is once again root 2 over 2. Thus, our left-hand sum, approximation for the area underneath f of x from the interval from 0 to pi, is this value of pi fourths multiplied by the quantity of 1 plus root 2. And there we are. That is our left endpoint sum approximation. Now, what if we want to do a right endpoint approximation? Well, for the right endpoint approximation, r sub 4, once again, we're going to do delta x multiplied by f of x. In this particular case, the right endpoint is going to be f of x sub 1 plus delta x multiplied by f of x sub 2 plus delta x multiplied by f of x sub 3, and finally delta x multiplied by f of x sub 4. Since all the delta x's are the same, we'll factor that out as pi fourths. Sine at x sub 1, which is just pi fourths, plus sine at pi halves, plus sine at 3 pi fourths, plus sine at pi. And once we go through the whole evaluation process here, we are going to once again get the exact same value of pi fourths multiplied by 1 plus root 2. Now, in general, left endpoint sum is not equal to the right endpoint sum approximations. In this particular case, we do get that they are in fact the same because we have that sine of x on the interval from 0 to pi is going to be symmetric. And because of symmetry, we can definitely argue that the left endpoint and the right endpoint sums are going to be exactly the same. And as we can see, they are. Now, let's work on the upper sums. So for the upper sums, we don't have a formula for this. However, when we're looking at the upper sum, we want to make sure that on each interval, we go to the highest value on that interval, and that's going to create the height of my rectangle. So in the first rectangle, for this interval from 0 to pi fourths, the highest value for f of x occurs at the right endpoint, which is at pi fourths. my second interval, the highest endpoint happens at pi halves. My third interval, the interval from pi halves to 3 pi fourths, the highest point occurs once again at pi halves. And then finally, the last endpoint, the highest point occurs at the leftmost endpoint of 3 pi fourths. And so what we have here is we're going to factor out the delta x. That delta x, once again, that was pi fourths. And to evaluate each function at the given upper sums that we found, or at the given upper values that we found for every single interval, we're going to get sine at pi fourths plus sine at pi halves plus sine at pi halves plus sine at 3 pi fourths. Sine at pi fourths, that's root 2 over 2. Sine at pi halves, that's 1. Sine at pi halves, once again, is 1. Sine at 3 pi fourths, that's root 2 over 2. Which now means that our upper sum is then given by pi fourths multiplied by 2 plus root 2. So that's the value of the upper sum. We can do the value of the lower sum as well. And for the lower sum, again, we just want to look at in the interval, in each subinterval, what is the lowest value produced for that function output. So in order to find that, we look at the intervals. The interval from 0 to pi fourths, the lowest height is going to be 0, which means we evaluate at 0. Delta x, so for the next interval, we want to evaluate the lowest height on this interval from pi fourths to pi halves, and that's going to happen at pi fourths. Plus delta x going to the third interval, the lowest value occurring on this interval from pi halves to 3 pi fourths happens at 3 pi fourths. So that's where we evaluate the function. And then lastly, on the last interval from 3 pi fourths to pi, we want to evaluate where's the lowest height. That lowest height occurs at pi. Which then means my lower sum has an approximation of delta x, and delta x is at pi fourths, multiplied by sine at 0 plus sine at pi fourths plus sine at 3 pi fourths plus sine at pi. Sine at 0, that's 0. Sine at pi fourths, that's root 2 over 2. Sine at 3 pi fourths, that's root 2 over 2. Sine at pi, that's 0. Which means this lower sum is approximated by pi root 2 over 4. And according to the previous one of the previous observations of why we do upper and lower sums, we can then guarantee that the area underneath the curve is then bounded by the upper sum that we found, which is pi fourths multiplied by 2 plus root 2, and it's bounded below by pi root 2 over 4. That's what we can definitely conclude. And so we're going to be working with this type of conclusion as we move through this course. So I hope that you all enjoyed this lesson, and I will see you all for the next lesson, where we're still going to be talking about areas underneath the curve, but more specifically, we're going to define what it means to be an integral. Till then, stay safe.